All right, let's take a look at electric potential energy. And it is an energy, so we are looking at joules. And so let's look at a combination of, maybe 2-point particles. So we're looking at the energy here, which usually is a capital U for our potential, is K, Q1, Q2 over R, right? Pretty easy formula. There's lots of other variations we can look at. I guess I just want to remind you, if you're taking notes and writing formulas down, the potential energy is also just Q times V, because we've already established that the voltage, which is electric potential, the voltage due to a point charge is KQ over R. So then adding a Q to a voltage does in fact give you the energy then stored. So this will be more helpful when you really look at voltages, but not as helpful if we're just looking at a collection of point charges probably. So let's take a look at why this makes sense, when it's positive, when it's negative. So if we take a point charge located here, and we take another point charge from way over here, infinitely far away, and we bring it close. Why does this store potential energy? Well, these two things want to repel each other, right? So why do they store energy? Well, first of all, if you release them, what would it turn into? And it doesn't matter if you release both of them or release one of them. Again, this stored potential energy would then lead to kinetic. And so they ask a question like, well, what if you brought two protons to a certain distance apart? This distance would be R. How much energy would they have? Okay, well, the energy is right there. The potential energy that it would have is K, Q1, Q2 over R. Okay, now what happens if you let them release? Well, then all of that energy would then go towards kinetic energy. And the kinetic energy of both particles, and let's say they're the same mass. So if they're the same mass, they're going to end up accelerating the same, and then gaining the same velocity. And so you'd end up with like two things flying away. Eventually, if it was all kinetic, then you could figure out their velocity when they get infinitely far away. Okay, so we can do things like that. The energy stored here is also equivalent to the work done by you, right? The work done to be able to bring these two charges close together. Again, you're thinking about the one charge starts way over here, and you have to do all this work to get it to that point. Again, you have to do work. It's got no potential energy if they're infinitely far away, and then you bring them close, and how much energy you've stored is equal to the work you've done on that object. Okay, so the book likes to ask questions like, all right, what if there were three charges? What if there was a positive charge here, and a positive charge here, and another positive charge here? Well, how much work is done to get that thing set up? Well, you can think about it requires a certain amount of work or energy to do those two, to bring those two together, and then you have to bring this guy in, and you have to bring this guy in, and this one's fighting against it, and this one's fighting it. So you actually have three terms. The total energy stored here is K, Q1, Q2. We'll call this D, and we'll call this L, and we'll call this number 1, 2, and 3. So the potential energy of this setup is K, Q1, Q2 over D plus the work done to do these two setups, K, Q1, Q3 over L, plus the work done that has to be, so K, Q1, Q2, and this distance would then be what? Well, it would be the square root of V squared plus L squared. So that would be the potential energy in this charge configuration, okay? And again, that's putting all three there. Sometimes they only say, okay, these two charges, these two are already there and they're stuck. How much work is required to bring the third one in? Well, if you're just bringing the third one in and you're not accounting for these two original ones, then you'd only have this term. This right here is supposed to be, this was a 2 and a 3, so fix that, 2 and and 3, right? 1 and 2, 1 and 3, 2 and 3 are all the different combinations. So if you just had to bring this third charge in, you would just need these two terms because that was already there. But if you're putting all three charges in place, then the total work done. So what if I added a fourth charge? What if I added a fourth charge there? And I said, all right, how much work done to do all four of those charges? Well, then it's Q1 and 2, Q1 and 3, Q1 and 4. So there'd be an additional Q1, Q4 over this distance, and this distance and that distance are the same, assuming that this is some random rectangle. So that would be this, d squared plus L squared, plus Q2 and Q4 over that distance, which is L, plus Q3 and Q4. And that distance is D. So you have to be careful. Adding one more charge then, it makes this total thing a 6-term thing and ends up being just 3 factorial. So you have 1 and 2, 1 and 3, 1 and 4, 2 and 3, 2 and 4, 3 and 4. And again, you have to be really careful how they word the question. Are you looking for the work done or the energy stored in putting all 4 of them there? Or then sometimes, like I said earlier, sometimes they'll say, okay, the red charges are already glued in there. You've already done that work. How much work is required to bring a fourth charge in? Well, then you would just need these terms. You would just need the work done to bring in the 4, and the 4 fights against the 1, the 2, and the 3, which were these 3 terms. So I encourage you to read carefully. Okay? What happens if one of them were negative? Well, if one of them were negative, then one of these, is just negative. So let's say that, if 2 was negative, well then that would be a negative, that would be a negative, and what, those two would be negative, and that would be negative, sorry, 2 and 4. So 1 and 2, 2 and 3, and 2 and 4. Those terms would be negative, and again, it'd be negative work because that 2 actually wants to attract those positive charges. What if all of them are negative? Well, then all of these terms would actually still be positive because there'll be a negative and a negative and a negative and a negative, right? All negative and all positive are the same. So you don't really have to worry about negative signs too much. It's pretty easy. You just put a negative out in front if one's negative and one's positive. Okay, so this is kind of the potential, electric potential energy. And if they just say electric potential, they're talking about voltage. They have to use the word energy. And what are the units on all these things? Well, of course, it's in joules. It's a unit of energy. It doesn't matter what type of energy it is. It's going to be in joules, right? And again, whether they say the work done or the energy stored, it's really the same thing, right? The work is done by some external force kind of pushing this positive charge in. But once it's there, they would talk about the potential energy of that system. Okay? The other time they like to ask about potential energy, and again, this kind of goes into a video that you might have to look at, is if they talk about equipotential lines. So this is some line, this is some other line, this is some other line, and let's say this is at 10 volts, 20 volts, 30 volts. And they would talk about the work done, to move, let's say there's a 2 coulomb charge there, 2 coulombs of charge there, and how much work is it to move it from there to there? Right, again, we know that charges want to go down voltages, and so if we want to find the work done or the energy required to go from here to there, that's where we're really using that energy is equal to Q times V. And again, that V is really always a delta V, even though they don't say it, right? That potential difference. Potential difference implies that it's really always a delta V. So if you want to take 2 coulombs of charge and you want to move it from 10 volts to 20 volts, you want to increase its volts by 10, you're going to do 20 joules of work. Okay? What if I'm here and I want to go down to here? Is there any work required? No, because you're not changing the voltage. I don't even care what path you do. If you go like this and then like this, it's going to be negative work and then positive work. Or if you went this way, it would be positive work and then you get some negative work done. And if you just follow the equipotential line, there's no work done. And again, so they like to use this a lot, and again, you have to make sure that it's not where you ended up, it's that difference. So again, going from here to over here, how much work is required? First of all, it's path independent. It doesn't matter if I start here and I do this, doesn't matter, and I end up there, then the work done, or the energy required to do that, is the amount of charge, 2 coulombs, times the change in my voltage, which in this case would be 20, and that would be 40 joules of work that needed to be done. Okay? If you wanted to talk about the potential energy something has at any moment, well, then you can just do it, and then it is actually just QV. If I wanted to specifically talk about the energy here rather than the work done. So I guess occasionally you are talking about this. But again, these voltages are always relative to something else, or something else is here. And again, if I didn't mention this before, these what would be called equipotential lines. Right? There are lines that show equal potential. So everything on this line somehow is created by some sort of charge configuration is 30 volts. So 30 volts are there, 30 volts are there, 30 volts are there, such that moving on along an equipotential are the same. So this is very similar to a topographical map. Topographical map, where you have like elevation. Right, your contour lines on an elevation, so this is all at the same elevation. Okay? So electrical potential, typically not that bad. Again, it's an energy, it's in joules. Most of the time, you're looking at the energy stored by point charges. So Q1 and Q2, you can have 3-point charges, you can have 4-point charges. You can talk about the work done to bring one more charge in, or you can talk about the work done to bring all 4 charges together. This is certainly a nice relationship between the voltage and the energy, kind of going back and forth. But both of these are really for point charge things.